Hi everyone. In this short video, I will try and take you through some of the very simple concepts and applications for the plasma elimination half-life. Now, the concept of half-life is actually borrowed from nuclear physics and was used to describe the rate of radioactive decay. In pharmacokinetics, the decline in plasma concentrations was observed to be exponential and was pretty much regarded in the same way as the decay in radioactivity. Hence, we have the concept of the drug elimination half-life. This concept has stuck and is still very much in use up to today. Now, most people have no difficulties in defining the term half-life. It is merely the time taken for plasma concentrations to decline by 50%. In this case, we can see that the half-life is about 10 hours. In the linear pharmacokinetic model, the half-life and elimination rate constant are inversely related through the natural log of 2. Now, the plasma elimination half-life is arguably the most recognizable pharmacokinetic parameter that we have. Unfortunately though, most people are not very clear about how to apply the half-life to solving clinical problems. For example, how do you make use of the half-life information for an anti-epileptic drug? Perhaps things would be clearer if I could just take you through 4 very simple applications of the half-life. Point number 1. When asked about the half-life, many people would say, well, it tells you about the duration of drug effect. This is actually not correct. It tells you about the rate of decline of concentrations, but not the duration of effect. Imagine a car. Knowing the speed of the car does not tell you the duration of the journey unless you have information about the origin and the destination. Similarly, apart from the half-life, you need to know about the initial concentrations as well as the minimum effective concentration. In the case of the anti-epileptic drug, there would be a minimum effective concentration for seizure control. If and only if you knew this, it would be easy to compute the duration of drug effect. Here, the half-life is 10 hours and the duration of effect is 23 hours. It is clear here that the half-life cannot directly tell you the duration of effect. Now let me take this a little bit further. Let's say you double or half the dose. Would you correspondingly double or half the duration of effect? The answer is no. Take a look at these plots. When you double or half the dose, the duration of effect will increase or decrease by the value of a half-life respectively. Point number 2. Most drugs are dosed according to their half-lives. Well, at least approximately according to their half-lives. There is a practical reason for this. When the dosing interval is equal to the half-life, the fluctuation in concentrations at steady state is about twofold. By this, I mean the Cmax is approximately twice that of the Cminimum. This is a comfortable level of fluctuation that avoids excessively high peaks or low troughs. If the dosing interval increases, the fluctuations are amplified. Here, the dosing interval is twice the half-life and the fluctuation is fourfold. Now, if the drug is very safe, these fluctuations are not problematic. But if the therapeutic index is low, managing safe therapeutics can be difficult in the presence of such excessive fluctuations in plasma concentrations. Here, you can see the effect of decreasing dose intervals on the fluctuations. When the dose interval is half of the half-life, the fluctuations are only about 1.4. Incidentally, you should note that as long as the total daily dose remains unchanged, the steady-state concentration is completely unaffected by the changes in dose intervals. This curve summarizes the effect of dosing interval half-life ratios on the fluctuations at steady state. Increasing the ratio will reduce the swings, and vice versa. But bear in mind, there is often a negative impact of short dosing intervals on overall compliance to therapy. Point number 3. The time it takes for a drug that is given as a multi-dose regimen to reach steady-state concentrations is approximately the duration of 5 half-lives. Well, technically only 96.875% of steady state, but it's close enough for our needs. This is a mathematical reality. The thing to note here is, and as can be seen in this plot, even if you increase the dosing frequency, it will still take 5 half-lives to reach steady state. You can't speed up the process by increasing the frequency of dosing. If the half-life is long, time to reach steady state can be very long. This is something you have to bear in mind in planning your dosing strategy. If there is no urgency in treatment, you can allow steady state to be achieved in the normal course of treatment, which will be 5 half-lives. But if you think there is an urgent need to reach desired concentrations, a loading dose may be required. If you think administering a loading dose will shorten the time to reach steady state, you would be wrong, because it will still take 5 half-lives to reach steady state. The loading dose just narrows the gap between starting concentrations and the intended steady state concentrations. Now, point number 4. Lastly, we deal with the issue of accumulation. Whenever a drug is administered as a multiple dose regimen, some degree of accumulation usually happens. The accumulation here is defined as the ratio of the concentrations at steady state to that after the first dose. You can compare peaks or troughs, it doesn't really matter. The accumulation depends on the ratio of the dosing interval to the half-life. Here you have a drug with a half-life of 12 hours being dosed at the 12-hourly interval. The accumulation is calculated by dividing the trough concentration at steady state, annotated here by CSS, and the trough level following the first dose, C1. The accumulation here is twofold. Here the dosing interval is twice the half-life and the accumulation is only 1.3. Now you can see in this series of graphs that reducing the dosing interval relative to the half-life has the effect of increasing the accumulation of the drug. Once again, note that regardless of the dosing frequency and the resulting accumulation, as long as the total daily dose remains unchanged, the steady-state concentration is unaffected. The accumulation is only a comparison between the steady-state concentrations compared to the first dose concentrations. Even so, it is important to appreciate this accumulation because it tells you that the patient is not maximally exposed to the drug concentrations after the first dose, and that it is prudent to schedule a review of the patient when steady-state concentrations are anticipated. This is a plot of the accumulation of the dosing interval to the half-life ratio. The Greek symbol tau represents the dosing interval. When the dosing interval is equal to the half-life, the accumulation is twofold. Increasing the dosing interval relative to the half-life reduces the tendency of the drug to accumulate, while reducing the dosing interval increases the accumulation. The effects of the drug at steady state will be greater than observed after the first dose. Now let's end with a quick recap of the main learning points. The half-life tells you how rapidly the drug is removed. If you know the initial concentration and the minimum effective concentration, you can estimate the duration of effect. Commonly, drugs are dosed according to their half-life. If dosing interval equals half-life, plasma concentrations fluctuate about twofold around the steady-state concentrations. More frequent dosing results in less fluctuations and vice versa. It takes about 5 half-lives for concentrations to reach steady state. Changing dosing frequency will not change the time to reach steady state, neither will the use of a loading dose. Accumulation is measured by comparing steady-state concentrations with the first dose concentrations. Accumulation is dependent on the dosing interval to half-life ratio. The smaller the ratio, the more the accumulation. Okay, I hope you have found this session useful. Please continue to follow this channel and our other videos on elimination rate, nonlinear pharmacokinetics and clearance mechanisms. This is Ed Lee. I'll see you then.